It's time for our next speaker in the morning. And I'm very glad to introduce a speaker who actually at one time was our own undergraduate student here at Harvard. He's one of the young speakers here. He got his degree only in this millennium, 2001, from Christodoulou in Princeton, and he's now on the faculty of University of Cambridge on the other side of the Atlantic. He's going to speak on recent progress in mathematical general relativity.
So thank you very much, and thanks to the Clay Institute for the invitation to speak at this conference. So I've been asked to give a survey talk on recent progress in mathematical general relativity. I suppose this is meant to be a light intermezzo between more serious talks in logic and number theory. That being said, let me begin immediately with the subject. So we were reminded at the dinner yesterday that sometimes it's difficult to explain mathematics, let's say, to the person sitting next to you on the plane. But in the case of general relativity, it's actually very, very simple. You just have to recite the words on this slide. So let's do that, and that will be our introduction to the subject. At least for the purpose of this talk, general relativity, really it concerns four-dimensional Lorentzian manifolds, M, G, satisfying the celebrated Einstein equations. So these are the set of equations written here. So equations have a left-hand side and a right-hand side. So on the left-hand side is this curvature expression made up of the Ricci curvature tensor and, well, the scalar curvature tensor, some contraction of the Ricci curvature tensor. And this is set equal to this mysterious object on the right-hand side, which is known as the stress energy momentum tensor of matter. Now, sometimes one says that the left-hand side of this equation, this sort of geometric object related to the metric, is known as the marble, and the right-hand side of the equation is known as the wood. So it turns out that wood is much more complicated than marble, actually, to understand. And before I even begin to tell you anything about the wood, we're going to set the wood to 0. So for the purpose of this talk, then, the wood is 0. This is the so-called vacuum case, and a very simple exercise in linear algebra tells you that this system of equations immediately simplifies to Ricci curvature equals 0. So the study of general relativity from the point of view of this talk is really just the study of four-dimensional Lorentzian manifolds, which are Ricci flat. Okay? So that's what general relativity is all about. And the most important fact about these equations that we all have to swallow before we can say anything else is that this system of equations is hyperbolic. So what does that mean? More or less, that essentially means that they're like the wave equation, and thus they have a well-posed initial value problem. Okay? That's to say, the natural problem to ask is you set up initial data, and to every set of initial data, there's a unique solution. So if you want, this says that the right way to think about the theory is from the point of view of dynamics. Now, there is one little subtlety, which is in fact not so little, about all this, and that's the following. As opposed to the case of the wave equation, where you can set up arbitrary initial data, initial data for the Einstein vacuum equations is not arbitrary. You cannot freely specify it. It is also constrained, and it's constrained by an underdetermined elliptic system of equations. So somehow both hyperbolic PDE, but also elliptic PDE, they enter into this subgroup. So, if you will, the achievement of this point of view was not at all obvious when the Einstein equations were first written down, and really, to be understood, took, well, almost 50 years or so. And, well, somehow the fact that this is indeed the case, that the Einstein equations does admit a well-posed initial value problem, was finally resolved by Yvonne Choquet-Bras and, well, Choquet-Bras and Garrosh. And the statement is precisely that there is this notion of initial data set. You should think of initial data set as a three-manifold, and what will be the first and second fundamental form of the three-manifold in the solution four-manifold. And these have to satisfy these constraints. If you know your differential geometry, then you realize that these constraints are coming from the Gauss and Guardazzi equations. But let me not say any more about that here. Given sufficiently smooth initial data, there is a unique solution to the Einstein vacuum equations, what's called in the terminology of the field the unique maximal globally hyperbolic development spacetime. Now, this word globally hyperbolic, this is a concept due to Jean Leray, and we will return to this later on, but for now you can ignore those words. So maybe I should emphasize the following point, that if you sort of live in close proximity to theoretical physicists, then sometimes in any reference to this type of result, you will be told that, well, of course the solution exists, after all, we're all here. And, well, I will not comment on sort of the epistemological notions. Actually, the truth is that theoretical physicists are typically more sophisticated than that, but I'm also in close proximity to fluid mechanicians. This is certainly the type of things that you hear all the time. What I want to point out, though, is that the analog of this theorem is, in fact, not true for most alternative theories of gravity that one sees in the literature, including many alternative theories of gravity that are sort of very popular these days, which come out from high-energy physics. And it's quite miraculous that the Einstein equation satisfies this theorem, because the equations were not, let's say, written down with this theorem in mind. In fact, Einstein's view of the Einstein equations was not at all, let's say, from the point of view of dynamics and hyperbolic equations. He was very much inspired by Machian principles, which are, in fact, very, very different. So I emphasize again this point, then, that it really is the case that this sort of theorem, getting it right, required many conceptual issues in the subject to be understood. And this really was sort of, if you want, the main contribution of mathematical relativity in the first part of the 20th century. And as far as the issue of the constraints, the freedom in imposing initial data, this is something which was first studied really by Lichnerowitz in the 30s and has been studied by many people thereafter. Many important events in mathematics really are statements about precisely that problem, understanding how constrained initial data is, including maybe most famously the positive energy theorem of Schoen and Yau. And on the point of view of evolution, understanding that these equations are hyperbolic and the right problem to pose is exactly this initial value problem. Again, this was something that was not really understood by Einstein. David Hilbert understood it maybe first, very early on, and he proved, in fact, well-posedness results in the analytic category already in 1918. And somehow this, how to see hyperbolicity, is related to the notion of gauge, and the correct gauges to impose were first understood by de Donder, and also with the notion of energy estimates, which is somehow one of the main contributions of the early 20th century nonlinear PDE in general to mathematical physics. So many fundamental conceptual issues have to be understood. And in both of these sort of questions at the sort of level of fundamentals, these are still very active fields of research, and there are very recent contributions that shed light on these somehow very general type of questions about the Einstein equations. So I could, in fact, in this talk, restrict the whole talk to precisely those questions. It really would also be, I think, an interesting talk. But it will be more entertaining, hopefully for this audience, to try to jump immediately, to fast forward, so to speak, to the celebrated physical conjectures, which are really the center of interest in the subject. If you want the dream results that we would like to understand about general relativity. So let me just say before leaving this prologue that we should always keep in mind that somehow all interesting questions in the subject, they are questions about the Cauchy problem. In fact, to formulate the questions, you need the language of the Cauchy problem. In fact, much of the confusion that sort of surrounded this field for many, many years was because the language of the Cauchy problem was not somehow suitably developed yet. So, in particular, the important progress that's still going on very foundational aspects of the Cauchy problem, well, this is actually intimately related to progress on all the issues that I'll talk about in this talk. But somehow I conjecture that perhaps understanding, let's say, in what Sobolev space one can prove well-posedness for the Einstein equations will probably not be so popular with this audience. So I will suppress these type of issues completely, even though you should know that they are always there in the background. Okay, so the rest of this talk will be, if you want, a tour of recent mathematical progress and hopefully future mathematical progress that may take a long time to happen in general relativity. And the way I'll try to set this out is in the form of 3 long digressions, I guess, long in the framework of the time allotted, hopefully. 3 long digressions which each start from a special explicit solution of the subject. That's to say, a special explicit solution of the Einstein vacuum equations. So this is a general, I guess, feature in mathematical physics that to really understand what the theory is all about, you have to understand a number of explicit solutions of the theory. They are very suggestive of more general phenomena, and typically the conjectures, they are conjectures that say that some of the phenomena that you see in explicit solutions is more general, or maybe it isn't more general. So this will be the point of view that I'll try to take. And well, what could be more special than Minkowski space as a special solution? Special precisely because, if you want, this solution predates the formulation of the theory of general relativity, and the Einstein equations in particular. And it was Minkowski's, if you want, fundamental insight, which was around 1908, that the physical content of Einstein's previous special relativity, this could be reformulated. So Einstein's special relativity was typically described in terms of lifts and trains, etc. But you could reformulate this as follows, as the statement that the equations of physics should have a geometric expression on the 4-dimensional R4 with metric this expression. Okay? So this is precisely what defines Minkowski space, and well, this is the simplest example of a Ricci flat manifold. Now, it's entertaining to remember that actually when Minkowski's work came out, Einstein said that this is a typical thing that pure mathematicians do when they sort of get their hands on new things in physics, and he thought that it was, well, this expression here in German. But he realized his error, and somehow, whereas for special relativity, if you prefer to think in terms of lifts and trains, that's okay. It really is equivalent. It's much more difficult to formulate a general theory of relativity on the basis of sort of localized lifts and trains. Okay, so this is the most, if you want, special of special solutions of the subject. So let me make some comments about Minkowski space and sort of its place in the more general sense of things. So Minkowski space is flat. So in particular, it's the simplest example of a more general class of spacetimes that we'll call asymptotically flat. So these are spacetimes that are not flat, but if you go very, very far away, they are flat. In particular, they have an end, which is diffeomorphically R3 minus a ball. such that as you go out to the end, the metric becomes more and more flat. So just to clear up possible misconception, space-time in general relativity does not always represent the universe. Typically, space-time in practice, and certainly when one talks about asymptotically flat spacetimes, it only represents the universe in the vicinity of an important self-gravitating system. So you should think of somehow the notion of an asymptotically flat spacetime as an idealization for saying we are only looking at spacetime in the vicinity of some important object, think collapsing star perhaps, all right? And sort of everything that's very far away, we're pushing it to infinity. Okay? It's very important in physics to have a notion of isolated system after all. If you cannot discuss isolated systems, then you have to, whatever you're doing, you always have to study cosmology, which is more difficult. So what you should think is that infinity, the right notion of infinity, corresponds then to faraway observers, let's say us, we who are far away, and who receive gravitational radiation. So you should think of sort of the hyperbolic nature of the Einstein equations, the fluctuations of the metric, all right, from the source. Okay? So the right way to think about this issue of gravitational radiation and what it looks like, what are the right concepts, this, again, took a long time to develop. Again, the story actually begins with Einstein, who was the first, very early on, to understand that his theory predicted gravitational radiation. And you should think of this as really just the statement that the equations, in some sense, linearize to the wave equation. But he actually backtracked a few years later and believed that somehow this is related to the problem of gauge, that actually the equations didn't. So the modern point of view is based on important later insights that in some sense go back to Fock, TRAUTMAN, BONDI, and finally Penrose. And really to understand the right picture, the most useful picture for how this is set up, we owe this to Roger Penrose. And it's essentially the following conformal picture, which I'll try to describe. So you can remember that 3 plus 1 dimensional Minkowski space is spherically symmetric. This is sort of the approximate symmetry you should always have in mind when thinking of Minkowski space as something asymptotically flat. That's to say, sort of, the space-time associated to an isolated self-gravitating system. Of course, here there's no system, but in any case, you should think of it as, let's say, spherically symmetric as opposed to having planar symmetry. So it's spherically symmetric. So in particular, you can consider the two-dimensional Lorentzian quotient. That's to say, you quotient by SO3, the group action associated to spherical symmetry. That's another way of saying that you can consider the TR plane, where R is your usual sort of radial coordinate associated to a choice of polar coordinates. So it's actually a half plane, remember, when you look at polar coordinates, R is greater than or equal to 0. Okay? So you can look at this object, let's call it Q, and this Q, okay, this is a simple 1 plus 1 Lorentzian manifold with boundary, the boundary being R equals 0. So this Q, we can map it conformally as a bounded subset of 1 plus 1 dimensional Minkowski space. So this is another way of saying that you can, in some sense, topologize in a certain way infinity corresponding to this quotient in a way that respects the conformal structure. Now, why is the conformal structure important in Lorentzian geometry? Well, the conformal structure in Lorentzian geometry is equivalent to the so-called causal structure. That's to say, a map that preserves the conformal structure, it preserves the past and the future of every point. So the past of a point in Lorentzian geometry is simply, maybe I should say the future first, better to be optimistic. The future of a point in Lorentzian geometry is the set of all points Q, which can be connected to P by a causal curve. That's to say, a curve whose tangent vector is time-like or null. So the whole point of Lorentzian geometry, after all, is it allows you to distinguish between vectors which are time-like, null, or space-like. Okay? So this allows you to define the so-called causal structure. And it's very easy to see that somehow the causal geometry is somehow equivalent to the conformal geometry. Okay, so to make a long story short, then this object, that's to say the map of this quotient spacetime Q, conformally mapped into 1 plus 1 dimensional Minkowski space, is the so-called Penrose diagram of Minkowski space, and it's depicted here. So somehow if you understand this picture, then you have immediately understood an important thing about relativity. So let me just say, and I will explain it also on the next slide. So the Penrose diagram looks like this, and remember, the whole point is that you can read off by sight the causal structure. That's to say, if this is a point P, my hand unfortunately is not sturdy enough to really do this. This is a point P, then we find the past of P by drawing the lines at 45 and 135 degrees backwards. So that's this line, and that's this line, and shading in what's inside. Okay? That's to say, we can read off the past and future of a point just as if we were in Minkowski space. And somehow, moreover, the whole point of conformally embedding this as a bounded subset of 1 plus 1 dimensional Minkowski space is now we have an additional boundary, this boundary here, which is induced by this embedding. And moreover, we can also talk about causal relations specialized to the boundary. Okay, so now I can also look at this point, which is on the boundary, and say what is its past, etc. Okay. So let me tell you a little bit about that boundary, because in some sense we can distinguish the various components of this boundary on the basis of the behavior of the function r. Okay, so now this r was originally the coordinate of a sort of polar coordinate system. But if you want to be more geometric, you can think of it as follows, that this picture, every point is a sphere, except for the points where r equals 0, which are points. And the sphere has an area. You take the square root of that over 4p, the Greek p. That gives you r. Okay. So you can distinguish the various components of the boundary. Someone told me that I would forget this open and start flashing it at the audience, but I didn't listen. So you can distinguish the various points of the boundary on the basis of the somehow behavior of R. So in particular, you can consider those points on the boundary which are the limit points of future directed null curves in this quotient for which R goes to infinity. Okay? That set of the boundary is this set here, and this is known as future null infinity. Sometimes, if you live very close to Oxford, it's known as scry. Okay. But in Cambridge, we call it future null infinity. Okay. So future null infinity is the boundary at infinity which is associated to the radiation regime. That's to say, if you think about solving the wave equation on Minkowski space, and you look at the asymptotics of the solutions of the wave equation, all right, then the non-trivial asymptotics are here. Okay? So in particular, gravitational radiation, that's something which is defined at future null infinity. To think about it another way, if you thought of this as sort of a self-gravitating system, forgetting that it's actually a very trivial one, all right, and we were measuring radiation from it, then we would be on future null infinity. So future null infinity is somehow the most important part of the spacetime from this point of view. So, well, you can replace the word future with the word past in all this discussion, and you obtain something known as past null infinity. So these are the limit points of past-directed causal curves, which go, again, for which R goes to infinity. And then you have these remaining points, which have the names that I've told you here. So we can do a little exercise that will be maybe useful later on in the talk. And that's the following. So you can ask yourself, well, what is the past of the whole of future null infinity? That's the union of the past of all the points on future null infinity. Well, what's the past of this point? It's everything south of this line, right? What's the past of that point? It's everything south of that line. So the past of the whole of future null infinity is, well, the whole of the spacetime. It's another way of saying that all points in the spacetime are visible to very far away observers in the radiation machine. Okay. We'll get back to that exercise later on. So, this being said, I promised a tour of important issues in the field, which is in the form of digressions on special solutions. So, in some sense, the most basic question you can ask about dynamics in the field is the stability of Minkowski space. So what is this question? Well, Minkowski space is special solution of the Einstein vacuum equations, as we said. So think of it as the solution that happened to arise from Madame Choquet's theorem on well-posedness from trivial initial data. Okay? So, in particular, if your initial data is Euclidean R3 with vanishing second fundamental form, then you get Minkowski space. So think of Minkowski space like that, dynamically. Now, perturb the initial data ever so slightly, and Madame Choquet tells us that there's, again, a unique solution of that data. What does this look like? In particular, does it share the features of Minkowski space? Does it approach, in some sense, asymptotically to Minkowski space? So this you should think as being the most fundamental type question you can ask about the dynamics of the Einstein equations, and its resolution is a celebrated theorem of Christodoulou and Kleinerman, which was published in 1993 as a monograph. And the statement is, yes, if you consider suitably small asymptotically flat data, which is suitably close to trivial data, and you consider the unique solution of the initial value problem, then it does share properties of Minkowski space. In particular, it's geodesically complete, like Minkowski space. And in fact, it approaches the Minkowski metric in all causal directions. Actually, the theorem tells you much, much more. It better because it took 500 pages to prove. So in particular, it tells you that this Penrose diagram, this picture that we drew for Minkowski space, you can in some sense reconstruct it for perturbations of Minkowski space. In particular, you can define a notion of null infinity, which you certainly cannot do in this very pedestrian way we did for exactly Minkowski space. And you can define all the quantities which are associated to gravitational radiation, and you can make rigorous the so-called laws of gravitational radiation that were first proposed by Bond. So this is really the first type of result, in some sense, about the global dynamics of the Einstein equations. So sometimes people ask you, why is Minkowski space stable? No one wants to read a 500-page monograph. So why is Minkowski space stable? And the sort of one-slide summary of why Minkowski space is stable is simply the following. It's stable because perturbations, in some sense, they radiate. They radiate precisely to this future null infinity, and they decay fast. Okay? And somehow you should think that the way you prove these nonlinear stability results is you somehow think of the perturbations as an error term, and it's very important that this error term, you can integrate it in time. So it's very important that this error term not only is small, but decays. And moreover, that it decays suitably fast. And here is the interesting thing, that in the case of Minkowski space, the rate of decay is just fast enough. It's exactly borderline. So in particular, if we lived in, let's say, 4+1 dimensions or higher, that we're told sometimes, then one of the advantages would be that the proof of stability in Minkowski space would be much, much simpler. It would be maybe sort of using modern technology, nonlinear wave equations, not more than 4 or 5 pages. So it's really difficult because of the lowness of the dimension, if you want. So let me just say that in these type of arguments, understanding perturbations, it's not sufficient to understand perturbations on exactly Minkowski space. That would be, in some sense, the physicist way of trying to prove stability. You would look at first-order perturbations, and then you would look at second-order perturbations, and then et cetera, and you would try to sum it all up. But that's never what you do in nonlinear PDEs. you actually work in a form of continuous induction known as bootstrapping, which essentially means that you have to understand perturbations on the spacetime that you have, which is a perturbation in Minkowski space. And somehow, if you can understand perturbations on perturbations of Minkowski space, then you can close the argument. And it's actually quite interesting that even though the sort of study of, let's say, how do waves decay on exactly Minkowski space is the most classical of problems in analysis, and certainly was studied in the 19th century using stationary phase and properties of fundamental solution, this is actually inadequate for understanding the decay of waves on perturbations of Minkowski space. And a new set of methods had to be developed, which in some sense goes back to Moravec. It was extended by Fritz John and then Kleinerman and Christodoulou. And this other method, known as the vector field method, is actually more elementary than sort of the more classical methods, but it's thus more robust, and somehow all sort of stability results in nonlinear wave equations, they go through this understanding. So let me also mention that there are some new developments in the field of stability of Minkowski space. There are simpler proofs of versions of the results by Lindblad Rodniansky using harmonic gauge, and by Lydia Beery also. So, okay, so much for digression 1 surrounding the first explicit solution that I wanted to talk about, namely Minkowski space. So let's go on another.
When you say physicists, they make linear perturbation, and then how do they convince themselves it's globally stable, or they just say it's linear?
Well, they just say that it's globally stable.
But they do try some infinite series?
No, I mean, they never do it in practice. I think that's how they would imagine. I think that's more what they imagine that we would be doing.
Sure.
No one ever does that, of course.
That's very generous.
So, the next, let's say, most basic explicit solution of the Einstein vacuum equations is the so-called Schwarzschild solution. So, actually, I just lied. It's not a solution. It's actually a one-parameter family of solutions. The parameter is called, let's call it capital M, okay? And these solutions are spherically symmetric, like Minkowski space, and static, like Minkowski space, but they don't have the additional translation symmetries of Minkowski space. So these solutions were discovered immediately after the formulation of the Einstein equations, already in 1916. And, well, in local coordinates, very easy to write them down. The metric takes this form. So if you're bored in this talk, you can just compute that this is a Ricci-flat family of metrics. So you'll notice that this is a form of what you might think of as polar coordinates. And you should think that originally, the way this metric was viewed by Schwarzschild is as the vacuum region outside of a star. That's to say, you should think that you actually consider this metric in the region little r is bigger than or equal to some big R. So that's the vacuum region. And inside, the region r is less than or equal to little r. Well, you have a star, so you shouldn't have a vacuum metric. And in fact, Schwarzschild showed that you could glue this metric to a solution of an Einstein perfect fluid system. That's a reference to the wood. So this is really what originally this was supposed to be. But certainly it seems to be a reasonable question to ask the following thing. Let's forget about the star. Let's just look at this metric, and let's look at what is the natural underlying manifold on which this metric can live. And immediately you see that, of course, something is wrong with the metric functions in this coordinate system in particular. If you set r is equal to 2m, then the coefficient in front of dr squared just blows up. So this caused lots and lots of confusion. And the final elucidation of this issue gave rise to the black hole concept. Now, actually, one of the sort of most mysterious aspects of this story is not that it took so long to be elucidated, which in some sense one can understand, but it's that it actually had been elucidated, but no one really paid any attention. So, in fact, somehow the in retrospect, what is the correct way to view this problem was really understood already by Lemaitre in the early 30s. But somehow this really was not noticed. So again, I will fast forward a bit to the solution of this problem, and I'll make use of this sort of notion of Penrose diagrams, because this is by far the most succinct way of conveying the information. So when we now say the Schwarzschild solution, we always refer to somehow the maximal extension of the original metric. That's to say that the metric on the biggest manifold in which it makes sense as a vacuum spherically symmetric solution to Einstein equations. Okay? So this was actually first discovered by Singh in 1950 in a paper that was published in a rather obscure Irish journal. So Singh is actually the father of Kathleen Moravitz, who I mentioned earlier. But it really only became popular with another paper of Kruskal, which appeared 10 years later. And so this is often known as the Kruskal extension. And the Penrose diagram of it, so this is again, remember, this is a spherically symmetric family, so you can take the quotient as before by SO3, and you can conformally embed into 1 plus 1 dimensional Minkowski space, and you get this. So let me tell you a few things about this. So first of all, it may help if I tell you, it's somewhat confusing when you first see it, because there's two of everything, it seems. Well, this is related to the following fact. So if you look at a Cauchy hypersurface, so a Cauchy hypersurface projects to something like this. All right. Then the Cauchy hypersurface does not have topology R3, but rather it has topology R cross S2. Okay? So this is a manifold, the Cauchy hypersurface, the 3 manifold, would be a manifold with 2 asymptotically flat ends. And because there are 2 asymptotically flat ends, there's 2 of everything. So in particular, future null infinity, that all-important object in the theory, it has 2 connected components. But let that not bother us. We can discuss that issue in a bit. We can still very easily do the following exercise. We can look at its past. So the past of future null infinity is very easy to see. Everything south of this or south of that. That's to say, everything south of this V. Okay? That's the exercise we were doing previously. But now you see that the past of future null infinity, it has a non-trivial complement in the spacetime. That's to say, everything which is north of this V. All right. So in general, the complement of the past of future null infinity is what we call the black hole region. So to say it another way, remembering that future null infinity means faraway observers in the radiation zone, then black hole region just means it's a region of spacetime with the property that it does not send signals, cannot communicate with faraway observers in the radiation zone. That's what black hole is. Okay. So let me just say the following comment, that you shouldn't think that the notion of black hole is somehow inherently related to non-trivial topology of the data. In fact, the physical picture of a black hole solution that you should have, and now I will return to the wood just for a second, is that you have, again, a collapsing star surrounded by vacuum. Okay? So you should think that collapsing star is the darker shaded region, and the vacuum is then Schwarzschild. Okay? It turns out that if you have a collapsing spherically symmetric star surrounded by spherically symmetric vacuum, the vacuum region is always Schwarzschild. Okay? So you should imagine a Penrose diagram that looks like this, where you have some matter which is supported in the darker shaded region, okay, and where, well, this is precisely a patch of that other spacetime that I showed you there, and these are glued together. Okay, this is really the physical picture of a black hole. So actually, this type of spacetimes were originally constructed by Oppenheimer and Snyder in another prophetic early paper in the subject that appeared in 1939 as solutions of the Einstein dust system, where the dust is the wood. And one nice thing about this Penrose diagrammatic notation is certainly this picture conveys everything you need to know really about the geometry of those solutions. In fact, it would have been very useful had these pictures been available at the time. I think the paper would have been understood much, much earlier. So this is this is the picture you should have in mind of black holes, that you have a null infinity with a property that if you look at its past has a non-trivial complete. So this being said, let me say something else. The Schwarzschild and Oppenheimer-Snyder spacetimes, they have another funny property besides the property of having a black hole. The other funny property is that they are geodesically incomplete. In fact, all geodesics that enter the black hole are incomplete. That's to say, if this is a time-like geodesic, it goes like this, and it enters the black hole like I've depicted, then it's incomplete. That's to say, its length will be finite. And similarly in Oppenheimer-Snyder. All geodesics entering black hole are incomplete. Again. Okay. So it turns out that this geodesic incompleteness is a stable property. So what do I mean by that, and how can we capture that? Well, to capture that, I have to introduce very, very briefly a notion. That's the notion of a closed trapped surface. So you should think of a closed trapped surface as being a two-surface. So this is a two-surface. I mean, you can think of it as a two-sphere if you want. It's important, but typically this will be the situation in your four-dimensional manifold with the following property. If you look at its future, so let me draw this like this. If you look at its future, then its future locally looks like this. You take two cones, okay, and you shade in sort of what's in between the cones. Okay, this is what the future of a two-surface looks like in a Lorentzian manifold. So you can look at the cross-sectional area of the two surfaces as you move it along the outer cone and as you move it along the inner cone. And, well, in Minkowski space, if you look at this cross-sectional area as you move in the outer cone, it increases. And if you look at the inner cone, it decreases. So that's typically what you might expect. So a trapped surface is simply a surface for which, in both directions, this cross-sectional area decreases. So it turns out that if you look in both the Schwarzschild and Oppenheimer-Snyder, that each of these points in the Penrose diagram, remember these points are spheres upstairs, so all the spheres inside the black hole region are actually trapped surfaces from this point of view. Okay? So that's the notion of a trapped surface. So this stability of the property of geodesic incompleteness follows then from the following theorem of Penrose, which was quite remarkable. So it says the following. Suppose you have a globally hyperbolic spacetime with a non-compact Cauchy surface. So certainly any asymptotically flat Cauchy surface is non-compact. All right? And this has nothing to do with PDEs. This is really a result in comparison geometry. Suppose the Ricci curvature has this positivity or non-negativity property. So in particular, of course, if it's vacuum, if you're Ricci flat. Okay? Then the statement is the following. If the spacetime contains a single closed trapped surface, then it is futurely causally geodesic complete. Now, because somehow this notion of trapped surface is defined by inequalities on a notion of mean curvature, that's manifestly on a compact set. This is manifestly stable. That's to say, if you have a solution which has one of these, and you think of it as a solution of initial value problem, and you perturb initial data, then close-by solutions will also have this property. Okay? So this tells you that this geodesic incompleteness is a stable property. Okay? It's not, in particular, a result of the symmetry. So actually, in the beginning of this subject, it was really thought that all these pathological properties of these solutions were because they were very symmetric. And this is the theorem that somehow tells you this is not the case. Now, there's one other aspect of the incomplete geodesics which is worth mentioning, and this is again in both Oppenheimer, Snyder, and Schwarzschild, that incomplete geodesics like this, there's a reason why they're incomplete, or at least there's a reason why. There's something which is also true, which you might think is the reason why they're incomplete. Namely that the curvature blows up as you approach the maximum of their affine parameter. Okay? Another way of saying that is the following. This boundary r equals 0, you should think of it as a singular boundary, where the curvature of spacetime is blowing up. Okay? And all these incomplete geodesics, they move towards this singular boundary. So a priori, you might think that somehow the reason that you have geodesic incompleteness is because of singularity. And this thought is so persuasive that this theorem of Penrose is typically known as the singularity theorem. But we will see later on that maybe that's not such a good semantic decision. So let's, in fact, would help the field very much if everyone referred to this theorem as the incompleteness theorem. Because this is what the theorem tells you, that your spacetime is geodesically incomplete. Okay. So let me say one other thing about this incompleteness. So I already told you that the incomplete geodesics in both these examples are precisely those geodesics that enter the black hole region. Those are the ones that are incomplete. The geodesics that do not enter the black hole region, they in fact are complete. Well, there's another way of saying that, which is not actually exactly equivalent, but it's actually the sort of the better way of saying that. That future null infinity in both these examples, Schwarzschild and Oppenheimer-Snyder, future null infinity is itself complete. So you can think that there's a natural affine connection that you can define in the limit on future null infinity. And it so happens, you can't really read this from the diagram. I have to tell you that it's true, that this future null infinity is complete. So this is, in some sense, a way of saying that observers who are here, they live forever. Observers who are here, they live forever, while observers that go like this, they die in finite time. Okay? So that's true about both Schwarzschild and Oppenheimer-Snyder. And in some sense, another way of saying those words is that this incompleteness is hidden from faraway observers. Okay? So faraway observers never see incompleteness. Now, this happens to be true, but it might not have been true. I mean, you certainly can imagine a situation where you have a singularity, so you have in particular incomplete geodesics, such that this is seen by future null infinity in finite time. Another way of saying that is that future null infinity itself, if you look at this induced affine connection, that's not complete. So such spacetimes we say would have a naked singularity. Okay? You can actually construct naked singularities very easily by looking at Schwarzschild metric with negative mass. So I told you that Schwarzschild was a one-parameter family of metrics, and the parameter is m. So if m is negative, then you see naked singularities. But those metrics, however, don't have a complete Cauchy surface. So in some sense, they are examples that the problem of dynamics immediately excludes. But in principle, you could have a sort of dynamically arising naked singularity spacetime, which would have Penrose diagram like this. So that brings us to a very important conjecture in the subject known as weak cosmic censorship. And, well, to prologue it, let me just say the following, that if these naked singularities occur, that's a big problem for the theory. Because essentially it tells you that the theory predicts that under some circumstances that faraway observers, their time ends. Another way of saying it is the theory cannot predict what happens to faraway observers after some finite time as measured by these faraway observers. That would be awful if that were the case. Particularly, we don't see that phenomena, so that may encourage us to question whether this is really a good theory, general relativity. So in response to that, Roger Penrose formulated a very famous conjecture known as weak cosmic censorship. And this says the following: for generic asymptotically flat initial data, for reasonable Einstein-Mather systems, so if you don't want to think about the wood, let's just restrict to vacuum, then the maximal Cauchy development will always possess a future, possess a complete future null infinity. Okay? So this is another way of saying that generically you don't have naked singularity. So the best result in this direction says that this is true for the Einstein scalar field system, so where the wood is the simplest type of wood, namely a scalar field, if you restrict the whole conjecture to spherically symmetric data and spherically symmetric solutions. Now, the reason that you have to include the scalar field, I'll mention it very briefly in the next slide. Moreover, he showed that the assumption of genericity is necessary. That is to say, he also constructed explicit examples of dynamically forming naked singularities. So, let me give a short epilogue on the Oppenheimer-Snyder solution concerning trapped surface formation in the vacuum. So the Oppenheimer-Snyder spacetime is maybe the simplest example of a spacetime where a closed trapped surface forms dynamically. So if you look at this picture of the star, then it turns out that these surfaces here, these are trapped surfaces. But in the initial data, there are no trapped surfaces. Okay, so this is a very simple example of closed trapped surfaces forming dynamically. So this notion of dynamic formation of closed trapped surfaces was very important for Christodoulou in his spherically symmetric scalar field model. He gave a criterion for the formation of closed trapped surfaces dynamically, which plays an important role in this proof of this weak cosmic censorship conjecture. So in fact, weak cosmic censorship is really very strongly related to formation of closed trapped surfaces. But whether this could happen in the vacuum was completely open. And the reason is that the vacuum does not admit non-trivial dynamics in spherical symmetry. That's to say, if you write the vacuum equations in spherical symmetry, then the solutions are Minkowski space, which has no trapped surfaces, and Schwarzschild, which always has trapped surfaces sort of initially. So you cannot study trapped surface formation in the vacuum in spherical symmetry. So remarkably, in a recent monograph, Christodoulou was able to show that trapped surfaces do form dynamically for the vacuum. In fact, they form starting from initial conditions which are, in some sense, arbitrarily far from already containing a trapped surface. And behind this proof, if you will, is Christodoulou's very remarkable discovery, which I think will have many other applications for the Einstein equations, of a certain hierarchy in the nonlinearities in the vacuum Einstein equation, which allows you to strategically place a certain largeness into this hierarchy and follow this largeness all the way up to trapped surface formation without, in some sense, allowing the nonlinearities to go out of control and somehow prevent you from proving it. So let me just say that this sort of result has been further refined by Kleinerman and Rodniansky more recently. Okay, so very briefly, I think I started a little bit late. So let me do a brief tour of my third digression, which is at the basis of this introduction to some of the open problems and results in mathematical general relativity. And this will be based on the Kerr family of solutions. So the Kerr metric is now, again, it's not a single solution. It's a two-parameter family of solutions of the Einstein vacuum equations. And this family includes as a subfamily the Schwarzschild family of solutions. But its, in some sense, algebraic structure is much more subtle. And because of that, it was discovered much, much later. In fact, the reasons that this object exists as an explicit solution of the Einstein equation are, in fact, quite mysterious from algebraic point of view. So in any case, the parameters are called mass and specific angular momentum, and you can think of this as the metric associated to a rotating black hole as opposed to a non-rotating spherically symmetric black hole. And, well, again, you can write down explicitly the metric, and if you care to, you can explicitly verify that this is indeed Ricci flat. So this is the metric in local coordinates. And the parameter range where the modulus of A is less than m is the sub-extremal black hole case. So very, very briefly, the Penrose diagram of this solution, well, maybe I'll give you the Penrose diagram in just a second. First, let me tell you something about the geometry of the exterior region. So you have vector fields d by dt and d by d phi. So whereas the Schwarzschild solution was spherically symmetric, this is only axisymmetric. So instead of SO3 and its associated killing Lie algebra of killing fields, here you only have axisymmetry. So you have only d by d phi. So what's very interesting about the Kerr metric is that d by dt, which in view of its name you might think of as being a time-like vector field, is no longer time-like everywhere outside of the black hole. So somehow, if you remember in the Schwarzschild case, the exterior region of the black hole looked like this. And in the Schwarzschild case, d by dt is a vector field that looks like this, and it's safely time-like, well, all the way up to the horizon, where it becomes null. And remarkably, what happens in the situation of the Kerr family is that there is a region caressing the boundary of the black hole, so caressing the so-called event horizon, where d by dt becomes space-like. So why is that bad? That means that natural energy quantities that you might associate to, let's say, waves on this background, the sign of energy associated to this killing field is no longer positive. So this means that controlling perturbations is much, much more difficult. So, well, I think I may skip a few comments. In particular, I wanted to talk a bit about the Penrose diagram of Kerr. And you may notice that the Penrose diagram of Kerr looks a bit different from the case of Schwarzschild. In Schwarzschild, the future boundary of the black hole region was singular, as we talked about, and it was in some sense space-like. And here, the future boundary of the black hole region is actually regular and null. That, in some sense, gives rise to another very famous conjecture of Penrose, which is known as strong cosmic censorship, and essentially says that this behavior is unstable. I'm not going to talk about that. I'll skip that conjecture, although it's something very interesting to see. Let me just say the following words, that this weak cosmic censorship conjecture about the naked singularities and their generic conjectural non-formation, and strong cosmic censorship, which in some sense tells you that, let me just say these words, that geodesic incompleteness is there because of curvature singularities, as opposed to something more pathological, which is in fact the case in Kerr. These conjectures will be here for many, many years to come. So this is not a plea to the Clay Institute to add these to the Millennium Problems. It's just a statement that somehow, were they to be added, I think it would be a very safe investment. Nonetheless, let me very briefly close with two simpler problems concerning black holes, which are suggested by the Kerr solution, which have a much better chance of being resolved in the next 5-10 years, namely the uniqueness and stability problems of the Kerr family. So very, very briefly, the problem of uniqueness. See, we would like to characterize at least the stationary black hole type solutions of the Einstein vacuum equations. Because if we don't, then this list could go on and on. I mean, we've already seen the Schwarzschild and this larger family, the Kerr family. Well, maybe there's some larger family of stationary vacuum black hole solutions that is included here. So you'll recall for a second that these Kerr black holes, they are stationary and they are also axisymmetric. So it turns out that in the class of stationary axisymmetric solutions of the Einstein vacuum equations, these are unique. And this is a celebrated theorem which is due to Carter, Robinson, Papapetru, and there are more recent improvements. And actually this nice problem is really, in disguise, a somewhat non-standard uniqueness for harmonic maps with a non-standard boundary condition, which is singular. But one would like to make a similar statement without assuming axisymmetry. I mean, one wants to know that stationary black hole spacetimes, there are only Kerr. That somehow we've exhausted the list. And, well, it's been known for a long time that you can do this as long as you're willing to assume one thing, namely analyticity. That's to say, namely that you only discuss metrics which are C omega, which are analytic. So, in fact, why is this so? Because there's a celebrated theorem due to Stephen Hawking that says that analytic stationary rotating black hole spacetimes are necessarily axisymmetric. So then you can apply the previous result. So, okay, maybe for some audiences that's not such a bad assumption. In fact, it's a nice discussion between Stephen Hawking and actually Madame Choquet-Bruhat, which was recorded in the conference proceedings, where he tormented her with the phrase, isn't nature analytic after all? But if you work in hyperbolic PDEs, then nature being analytic is anathema, because analyticity is somehow against all sort of fundamental properties of hyperbolic PDEs, in particular causality. So it's certainly not the case that if you're studying hyperbolic PDE, you are willing to impose analyticity because you don't have, in particular, the domain of dependence property, etc. And actually, the reason that this argument works is that the assumption of analyticity, it kills what's maybe the most interesting obstruction or potential obstruction to this uniqueness, which is high-frequency stationary solutions which are supported on trapped null geodesics orthogonal to d by dt. So if you know your Lorentzian geometry, you may be surprised that there are null geodesics which are orthogonal to d by dt, until you remember that d by dt can in general be space-like. So it's precisely, if you want, the existence of the so-called ergo region in black hole spacetimes that give rise to this potential obstruction. So very briefly, there is an important new result on this problem due to Ionescu-Kleinerman and then Alexakis-Ionescu-Kleinerman, which gives you this uniqueness, at least in a neighborhood of the Kerr metrics. That's to say that the Kerr geometries, they are unique without assuming either axisymmetry or analyticity, as long as you only look at nearby metrics. But somehow the physical mechanism that would be responsible for a general uniqueness is unknown. So finally, the problem of nonlinear stability. So now that we know, at least in the neighborhood of the Kerr metrics, that the only stationary solutions of the Einstein vacuum equations are the Kerr metrics, then it's reasonable to hope that if we return to the initial value problem and think of the Kerr solutions as those solutions that happen to arise from Kerr initial data and now perturb this Kerr initial data, that the unique solution of the Einstein vacuum equation would settle down to something stationary, and there's nothing stationary near Kerr except for Kerr, so we would imagine that these solutions would settle down to the Kerr form. So this is the problem of nonlinear stability of Kerr. This is unfortunately still a conjecture. Let me just say that as opposed to the stability of Minkowski space, this conjecture has two very interesting features. One feature is that it's really only the exterior of the black hole that one expects to approach the Kerr metric. In fact, had I talked about strong cosmic censorship, then if that conjecture were true, the interior of the black hole metric in Kerr would have to be unstable. So this stability only is in regard to one part of the spacetime. But you don't know where that part of the spacetime is until you've solved the problem. Because the black hole region is precisely the complement of the past of future null infinity. And building future null infinity is, in some sense, the non-trivial part of this problem. So everything is somehow coupled. And the other interesting aspect of this problem is that whereas in Minkowski space there's only one Minkowski space, this is a two-parameter family. And if you perturb one Kerr solution, there's no reason why you should not evolve to another one, simply because the other ones are perturbations of Kerr, which are stationary. In particular, you cannot discuss separately the stability of the Schwarzschild subfamily. You have to consider the stability of this whole family, and you have to find a mechanism that tells you how you pick the future parameters. So let me just say that as in stability of Minkowski space, the difficulty in understanding this problem is understanding how linear perturbations decay on these backgrounds. And this is a classical problem studied for many years in the physics literature since the 1950s. But actually, until very recently, the state of knowledge of sort of even the boundedness properties of waves on, let's say, a fixed Kerr background was unknown. So you solve the wave equation on a Kerr background, just the linear scalar wave equation. It was unknown whether solutions grew or were bounded. And what you really need to know is that they decay. So in any case, let me close with this slide. So in the past 5 years, there's been rapid developments on this subject. And in particular, as a culmination of this, one can now state the following theorem, that if you look at the scalar wave equation on the Kerr exterior, that's to say on the exterior of the black hole, then solutions do remain bounded, and they decay, in fact, fast enough, in principle, for nonlinear applications. And what in some sense goes into this theorem is an interesting interplay between the celebrated redshift effect, so this is an effect well known to relativists that has to do with the event horizon. This problem of superradiance, that's to say the problem of d by dt becoming space-like. If d by dt didn't become space-like, it would be very easy to show that solutions remain bounded. And something known to people who work on the obstacle problem, classical obstacle problem, namely the problem of trapped rays, or in this case, trapped non-geodesics. And this field is maybe one of the most active currently in the interface between nonlinear waves on the one hand and geometric scattering theory, and there are many people who have contributed to this picture. So this gives some hope, at least, that the nonlinear stability conjecture for the Kerr family, at least this conjecture, may be amenable to mathematical proof in the years to come. So let me end with that. I apologize for going a little bit over. Thank you.
Are there any questions for the speaker?
In terms of the domains of dependence, is there any Huygens principle phenomenon where things, in odd dimensions, things pass you and...
You're talking about strong Huygens principle.
Yeah.
Well, certainly, with that type of thing, decay properties are different, let's say, in odd dimensions than in even dimensions. So there is a sense in which decay properties, let's say, in the interior, so decay properties, if you want, as you move towards here, as opposed to as you go in this direction, they are better in odd dimensions than in even dimensions. But in fact, that sort of refinement of decay properties is not so important for the nonlinear problems, simply because in the nonlinear problems, you typically want to prove the roughest type of decay, which is enough to prove, let's say, to integrate it. And this difference between odd and even dimensions, it sort of takes place, you see it at a finer level. And certainly in the nonlinear problems, you don't want to delve into that fine structure of decay, because somehow that just makes your life a lot more difficult without an improvement. But somehow this is certainly a general feature of wave equations, that you have faster decay than you might expect in odd dimensions. But certainly strong Huygens principle per se, that's to say that you have compact support in the... this is never true, essentially, when you perturb.
But it is true that singularities only propagate on the boundary?
Well, certainly, propagation of singularities, it's as you expect, along characteristics. Sort of, this is features of the standard features of hyperbolicity.
Are there other questions?